Okay, we're recording. I'm gonna hide this. All right. I think we're good. Great. So good morning, y'all. So again, it's week 10, last day of the quarter. It's been a pretty interesting quarter. Would you agree? Yeah. So I think we've done a lot this quarter, and I think y'all should be pretty satisfied. We started, not really comfortable with the software, and now I think y'all are pretty much good to go for the rest of your classes. So as I mentioned, today is going to be discussing differential equations. So we're going to do some initial value problems. The book also does boundary value problems. And then in the future, you might do partial differential equations. And then, but the majority of the class today will be focused on your projects. So I'll give you guys some tips. Raise your hand if you kind of got started already. Mostly everyone. All right, perfect. So thanks a lot again for joining. If you're on Zoom, let me just double check everything. Okay, great. So we're recording. So what kind of differential equations did you guys think of? Yeah, okay, good. Simple harmonic motion. Okay, awesome. So that's physics. Another one? Yeah, sure. Sure. Do you know about what kind of equations those are? Are they ordinary? Are they could be, yeah, like you could do some Taylor series expansion, or they could be like partial differential equations. Anything else? Fluids? Which ones are your favorites from fluids? Partial? Cool. I like them. So here are some that I thought of, in the context of calculus. We have, just the general form for a differentiable function. And then remember, the goal is we're going all the way back to week 1. We have to apply the fundamental theorem and then solve for these. In the context of physics, what equation is this? What law is this? Yeah, Newton's second law. But it's really a vector equation, and then hopefully you can see what are the, so this equation has constraints. What are the constraints of this equation? So if I want to go from here to here, what kind of information do I need? Yes, we need 2 of what? Two conditions. You remember what they're called? So if we're differentiating with respect to time, how many times are we differentiating? Okay, so we have second derivative, so therefore we need 2 initial conditions. So that's going to be your values at t equals 0, corresponding to your velocity and position. Okay. Similarly, this would be a first order rate equation in the context of chemistry. So you guys can probably pick this if you want to for your, I think someone else in the other class is doing some kinetics. So your goal is to solve for concentration as a function of time. So this is exciting for me because this is the premise of my PhD, is to calculate the rate profiles of different contaminants in water. So if you're interested in water, you can do something like that. And then of course, for a lot of us in engineering, what equation is this? Yeah, the mass balance equation. So you have your all your inflow rates minus your outflow rates. And then, what are some assumptions you can make to simplify this equation? Yes, no change in the mass over time. What is that called? Yeah, good. Steady state. So if you haven't seen this yet, surely you'll be a master all of these by the time you guys graduate. So that's exciting. So if it's steady state, then that's nice because this goes to 0. If it's non-steady state, then you got some homework. So again, you can, I suggest not to go with physics and calculus. I suggest to go more with the chemical systems for your projects. And you don't have to do ODEs. We'll talk more about those shortly. So just some ideas of some analytical solutions to equations. And then so today we're going to be doing, like I said, ordinary differential equations. So what's the difference between initial value and boundary value? So for initial value problems, we need some initial conditions. For boundary value problems, we need boundary conditions. So for initial value, we're differentiating with respect to dt. Okay, so that's today. We're doing dt. And then for boundary value, we're doing what? Differentiating with respect to, yes, x or y or z, dx, okay? So very simple. It's initial value, you need some boundary condition, initial conditions, and boundary value, you need some boundary conditions. Okay, so as usual, the book entails lots and lots of different objectives. I encourage you to, if you have time, even after the quarter, definitely still refer to the book. Can be very useful. I suggest going through the Runga because you might use it for your other classes. And then I believe the MATLAB functions, here we go. The MATLAB built-in functions, most of them, I believe, use the Runga method. So definitely try to check those out. And then that's going to be useful for your classes and then for your jobs probably. But today we're going to keep it simple. We're just going to do some background and like a really quick Euler's method example. All right, any questions before we do an example? All right. So I like the example in the book because it covers a, really nice mass balance problem. So we have cylindrical system, just a tank. We have the inflow, and then we have the outflow. And then, so our goal is to calculate the mass balance and then define the differential equation and then hopefully solve the differential equation. So we have some parameters. So what are the parameters in the system? Volume. Volume is not a parameter because it's a function of some other parameters. The flow out, okay, yes. All right, here we go. dm out dt. Height, yeah, there we go. Area. So all these terms, those are all the parameters. And so these are gonna be basically all the knowns. So if we have all our parameters, we know all the values, then we can solve the system. Otherwise, for your job and for your projects, your goal is to solve for these. And then, try to optimize the system. So how do we write the mass balance? Give me in the form of an equation, please. So what am I going to write? I think you're thinking of the production term. So in this case, the production is going to be 0. So we're not having any kinetics. So it's going to be, accumulation. I'm not sure if I said this in this class last week, but when in doubt, accumulation equals in minus out. So basically, it's going to be your accumulation. When in doubt, accumulation. Okay. I'd like if everyone start to write this down because this could be useful for your projects. You might have to write some mass balances for your projects. So just simply write When in doubt, in minus out. So this is your in. So this is what type of function? Yeah, trigonometric, got a cosine. So that just simply means that they're varying the inflow and then the outflow. Does anyone know where this equation comes from? So if we have density, we have area, and we have height, what does that look like? Yeah, it's going to be derived from your energy balance. So that's like Bernoulli's equation. This is the, I think you're going to have to help me out. Is this the Torricelli form? Perhaps? I believe the square root 2gh is the. Okay, all right. So so now what's the goal? What's the goal for, what are the characteristics of this OD? What are we trying to solve as a function of what? Yes, we have height with respect to time. So we have height, we have time in here, and then we have height in here. Okay, what are the constraints we need? So is this boundary value or initial value? Initial value, so we need some initial conditions, which would be what? Good, T naught corresponding to H naught. Okay, so I'm sure you know by now. Do you think this is possible in the context of this class? Do you think it's possible to solve this by hand? Is it? No, because we have a square root of H term here, so that's going to be pretty ugly. I certainly don't know how to solve that by hand. So, you know, the goal is to, of course, use MATLAB to solve this by hand. So we're going to do some numerical solutions. So again, we have our parameters for our system. So your goal for your project is to find these parameters. Hopefully, you find them in literature, and then you write your equation, you solve your equation, and then your goal is to develop the profile, the change in height. Okay. So any questions about that? All right. So we're gonna do some really simple examples. We're just gonna go over the main idea. The main idea is basically similar to all the other methods. We start by dividing into n subintervals. We select an x1 equals a up to an xn plus 1 equals b. So we can define that in MATLAB. And so the solution is discrete as usual. So we're gonna have a vector or a matrix, and then it could either be single step or multi-step. So single step just means that you're looking at the next one by one, next point, xi plus 1, and you already know your previous one. And then multi-step is just going to be the several other previous points. Okay, so the main idea is pretty simple, and it can be used to solve some pretty complex equations. And then there's also explicit versus implicit. So we'll talk about that shortly. So the main one is Euler's method. So you only need 3 equations. You only need your xi plus 1. So what is this? What is this going to be? It's your xi. Yeah, it's your initial x position plus your h. So what's your h? Yeah, your step size, good. And then your y initial corresponding to your derivative. So if you have the derivative, then you can calculate the next point. So you only need really these 2 equations, 1 and 2. Okay. So this is Euler's method. So it's not the most robust method, but it can get the job done for many of the equations. Okay. So our goal is to obtain a graph that corresponds to the solution of the differential equation. So our goal is to get a graph that looks like the true solution is the numerical solution versus the exact solution, which is the true solution rather. All right. Does anyone have an idea where this is derived? So let's say this is the first derivative, and then let's say it's going to continue. Where would it go after that? So this would be the 0th derivative, and this is the first derivative, and then it would be some other stuff. Yeah, second derivative up to infinity. So what equation is that? Say again. Taylor series expansion. Good. So you might have to use the general form in your other classes, so keep that in mind. But we have the equation here, so let's just do a simple example. So our goal is to solve this differential equation, and we have the bounds here given. Everything is given. And then we have 2 steps to compare, 0.1 and 0.01. So our differential equation, who can tell me how to solve this analytically? So this time I'm not testing you, I'm asking you because I believe you're gonna have to need some cosine and some trigonometric functions, if I'm not mistaken, right? To get your exponential terms. Remember from your math 46. Okay, so we can solve it analytically, and then you can do that for fun or not for fun. And then we're gonna compare that with MATLAB. Okay, so everyone write down these equations, and then we're gonna just solve. Okay. So this time, it's Friday. It's Friday morning. I'm just gonna give you the solution so you can copy this down. So for this type of solution, we have 2 scripts. We have 2 scripts. One is the function, which gives the solution. That's the first script. And then the other script is the one that calls the function. So does anyone have questions about this? Because this is part of the homework, and I know some of you guys are a little bit confused with that. That's all right, but that's just the main idea. You have one script that one script that defines the function. So we'll talk about this, and the other script that. So in this script, we're going to define all the parameters. We have a equals 0 and b equals 2.5. Okay, our step size is going to be 0.1. And then the initial, so this is our initial condition. Okay, so I have y x equals 0, which we're calling y initial. That's 3. So these are all our parameters. So let me put that here. These are the parameters. So either you have to define them or you have to solve for them. Look for them in the literature, look for them. You might have to do an experiment to solve for those parameters. And then you call the function. So it's going to call ODE Euler. So let's call this function. So it's saying, all right, ODE Euler. And then what are all these? So if this is the function, then what are these? So it's A and B and H. So these are the inputs, these are the parameters. All right. So let's see what ODE Euler does. So ODE Euler is going to call the parameters that we just defined, and then we're applying the algorithm. So let's take a look at the algorithm. So we divide into n intervals. So that's our n. We define the function itself. So this is our goal is to solve this. Our goal is to solve this equation. All right. So here's our equation. We define it as anonymous function. Okay. And then then we apply Euler's method. So Euler's method, we start from I equals 1 up to n, and then we're going to define our x value. So our xi plus 1 equals xi plus h. And then remember that the values call it at each of the terms. So that's our xi. And then our derivative is already given, so we don't have to solve for that. So that's great. And then we multiply by h. Yeah, and that's pretty much it. So any questions before we see what happens? So then the final step is just to plot the results. So here I'm comparing it with the analytical solution. And if we have a step size, we can see what that looks like. Okay, great. So we have our analytical solution versus our numerical solution. And then how do we make this a little bit better? A little bit more accurate? What do we change? Not increase. Yeah, we decrease the step size. Good. You run that again. 0.1, 0.001. All right. That looks a little bit better. I'll make it even smaller. And then I can expand. I'll go out to 25. Okay. So that's our solution. So the drawback about differential equations with MATLAB is that we have now a graph, but it doesn't give us the actual numerical solution. Okay. So again, we define our parameters, we call the function. So unfortunately, some of y'all didn't get some points for the homework, and that was because you wrote the function, you call the function, but you didn't define it. So you have to define this function. This is the list of functions, and then you call the function. And then some of you guys other way around. So you wrote the function, but you didn't define the parameters. You didn't call the function. So make sure you get all the points for that. All right. Any questions? All right, great. So like I said, we're solving these numerically, and then there's the analytical solution. So therefore, that's the premise of a lot of math PhDs today, is to solve differential equations. Have you guys heard of the Millennium problems? So one of them is to solve the Navier-Stokes equation. So if you solve a Millennium problem, you get $1 million. So that's great. But we can use computers to get the numerical solution. But you know, if you can solve it by hand, if you provide a proof to that theory, then you'll become famous in the math realm. All right. So give that a shot. Come back to me in a couple decades. All right. So that's pretty much it. And then I want to point these ones out because if you decide to go with ODEs for your project, I recommend going with ODE 45. So, you know, y'all are really smart. So just go into the book, go into the documentation, or better yet, just go onto YouTube, look up ODE 45, and then maybe one of the ODE 23s. These are probably the best ones to go with. And so you have to be careful with your parameters. So like I mentioned before, this is why I want you to read the Runge-Kutta methods, so you can see how it's derived. But these are pretty much the standards that everyone uses. I'm not sure about these ones. If you go with these, let me know. And then we can talk about the drawbacks. So each of these has their own benefits and drawbacks. But I recommend going with ODE 45. Okay, so these are the MATLAB built-in functions. All right, questions about that? All right, I think that's it. Pop quiz. What are the differences between algebraic equations and differential equations? Very good, very good. I love that. Yeah, great. So algebraic equation, you're solving for a single value at a single input, and then a differential equation, like Lexi said, you're solving for a family of functions, or just a single function if you have the bounds. Great. What about initial value versus boundary value? So initial value, differentiate with respect to time. Boundary value, differentiate with respect to space, time and space. Good. So with boundary value, you can have up to 3 dimensions for physics, up to n dimensions for the math. In theory, you can go up to infinite dimensions. And then the what about ordinary differential equations versus partial, which we haven't talked about, but a lot of you guys are asking me for literature that includes PDEs. So what's a partial differential equation? Exactly. So ordinary differential equation, you're differentiating with respect to a single variable at a time. A single variable, ddx, ddy. You can have multiple equations, that would be a system. But partial differential equations, now it's going to be a little bit more complicated. So this is an example of a partial differential equation. So does anyone recognize this equation in your classes? Maybe not yet. So on this side, we have the partial with respect to time. So U is arbitrary, but let's say it's temperature. So that's your hint. Pretend that U is temperature. And on the right side, we're differentiating with respect to X. So how many boundary conditions do we need? So we have d squared dt dx squared. So this is second order. So we need 2 boundary conditions. How many initial conditions do we need? We only need 1 because we're differentiating with respect to time. So this corresponds to time, and this corresponds to your X. Okay? So this is very similar to your transport equations. So you're going to see this a lot this year. If you haven't already, your Navier-Stokes, but specifically, this is the heat equation, heat transfer. This is the heat equation. So in your projects, if you decide, I recommend not going with, I know a lot of you guys are interested in the, like the environmental aspects and like, doing some heat transfer stuff. I don't want to discourage it, but it's going to be a little bit out of the scope if you decide to go with solving an equation like this. And so in the literature, I want to point out that you're going to see the Laplacian. So if you see something like this, my recommendation is to hold off for this project. So you're going to see some Laplacians of different functions. Maybe they're trying to solve for like the heat flow or like the concentration, things like that. Read it on your own time. I don't recommend doing it for the project. It's something to keep in mind for you the rest of the year. Okay. So now we know all the different types of, or several different types of diffie-Qs. And then that's pretty much it. Okay. Any last minute questions about differential equations? Great. All right. So let's do some quick lab announcements. We're basically working on the project. So here's basically some tips in our wonderful chemical and environmental engineering. MEC is pretty interesting because we're doing lots and lots of different stuff. Like we can go into the fluids realm, we can go into like environmental, air quality. Dr. Cocker, I was pleased to see on the homepage of the department we have our reactor. So as I mentioned, I investigate the kinetics of the water. So here's our ultraviolet reactor. I talked to a bunch of y'all already about the projects you guys are doing. Some of you guys are doing internships. Some of you guys have jobs. That's really awesome. So my recommendation is to select a project that you're interested in. So maybe if you're in a group of all environmental engineers, go with like an environmental engineering problem. If you guys all like heat transfer or something or fluids, then pick something that's within the scope. But yeah, that's the key, to pick something within the scope of the class, and then we'll talk about how to research some stuff. Yeah, projects are really interesting because with the homework, it's kind of like just homework. But the way I personally learn a lot from MATLAB is doing projects. So even after this class, keep doing projects. Here's a picture of me and my friends. And then we're going to talk about different groups that you can form. So let's talk about that next. So here's a tip. You can divide up the tasks. So if there's 3 tasks, essentially have research and background, you have the mathematics, which is your MATLAB, and then writing and conclusion, okay? So let's say we have team A. So we have 3 members in team A, and then one person does the first task, research. The second person does MATLAB. So, okay, the person that did research informs the person who's gonna do the math, and then the last person does writing. So you can do it like that. Another method is to do what team B is doing. So again, 3 people, maybe one person does like lots of research and they know a little bit about MATLAB. And then the second person, they don't know so much about MATLAB, but they prefer to do more about writing. And then the last person is going to be more like the coder. And then they can like split up the work like that. Hopefully you don't see something like this, but occasionally it's inevitable. 2 people do all the work. One person just sits back, gets some coffee. If that happens, well, unfortunately, you're going to have to write up who does what for the projects. And then, Dr. Varsanti takes that into consideration. So keep that in mind. And then, yeah, so hopefully you have your teams by now. And then that's just how it's going to be. Again, like engineers have this bad rap of being like antisocial nerds. But I think that's totally far from the truth. Engineers have to be good at the math, but also have to be good at communication. So we have to speak to other engineers and scientists, but we also have to speak to people, especially like if anyone wants to go in sales. If you want to go into sales, then how do you market the product and then communicate it to the client, or if you're trying to sell a product. Yeah, keep that in mind if you're more interested in like public speaking, things like that. All right, so we're gonna do a couple demos. So I'm gonna pull up my MATLAB. Just to give you guys an idea of something that you can do. Here's a wonderful project by my colleague, Alejandra. So this is, let me be clear, I'm not trying to scare you. I scared the other class. This is a graduate level project, but this is something that you can, get inspired from. So we're gonna have to read the instructions carefully, but so like this isn't required in this class. You might wanna have a title, have the abstract. Again, shout out to my friend. She was nice enough to share this project because it was very fascinating. This was modeling advection diffusion. So basically calculating the pollutants spreading across in air systems. And then, look, it's straight from the book. So that looks recognizable. So she used the finite difference method. and then she calculated the concentration profiles for the air pollution. Okay, so this is exactly what I don't recommend. If you start to see stuff like this, I recommend not to do that for this class because you only have until Monday. Okay, and then defining all the writing, and then finally the conclusions. Okay, so here's her MATLAB. It was a wonderful animation. You can see it spreading out over time. And then at the end, this is very important, is going to be your code. So your code and the references, and the code is going to be what you actually put in your script. Okay, so it's going to be like all her wonderful, long scripts. And yeah, so that's something to look forward to for your project. So again, this is a grad level. It doesn't have to be this extensive this time, but yeah, keep this in mind because that's how it's going to be for your senior design, things like that. And then here's my simple little script for, this was a, let's see, this was for one of the labs in undergrad here. So this was calculating the McKebb-Thiele profile for your distillation when you take separations. So you can do menus. All I want to show is the user-friendly aspect. So this is, again, not required, but if you play around with it, it's going to be useful and way easier for us to grade. So we can go through the code. I don't want to talk about what it does, but it does some calculations, and then it calculates the number of stages. So, you have a nice little menu. You click begin, and then the user can change the composition, the feed rate, and the reflux ratio. So again, not required, but it's encouraged to try it out. That's where MATLAB gets a little bit more fun. So we let it do its thing, and then it's still running, and then it calculates the number of stages. So there's nine little triangles here. Okay. So again, this is like optional, but if someone wants to go ahead and try this, it's going to be good for your experiences. And then you can add it to your resume, add it to your LinkedIn. You can share it for your classes. And then who knows? Yeah, who knows? Like maybe you start off with a little project, and then maybe it gets a little bit more. You do a startup. That's how lots of startups get started, right? I'm afraid, I'm not sure if the Zoom people saw that. You guys see that? Hopefully you did. All right. So those are some little demos. Hopefully you can take some ideas from that. So if you do just like a percentage of that, then that's totally fine. A couple more quick tips. Basically just manage your time. So if there's 3 tasks and you have 3 days, you want to go ahead and do 1 task per day. And then be really careful with your project selection. So if you haven't already chosen a project, what I really want you to do is do not leave the room until you choose a project. Let me know what you guys are working on, and then I'll say, yes, do that, or please don't do that. You need some sleep. Okay, answer the questions, get all the points. So carefully read the instructions. There's a couple little small things you have to be careful of, such as the writing aspect, more so about the writing aspect. So you have to do an introduction, conclusion, summary, etc. And then, as I mentioned, try to have a working script that's user-friendly. Or if it's not user-friendly, at least tell us, all right, here's the function, and then here's how you call the function. And then definitely provide some user inputs so we don't have to guess the parameters. All right. Yeah. Any questions about the project? We're gonna, you guys are gonna have time, and then I'll walk around as usual. All right. So yeah, that's pretty much it. I read you guys reflections. In the beginning of the quarter, y'all have different ideas. Y'all had different ideas about what this class entails. And then now it's 10 weeks later, and now you have a new skill you can add to your resume. Unfortunately, most industries don't use MATLAB. because it's really expensive. So you're gonna still be learning lots of other code. You might want to look into Python. The environmental engineers are going to do lots of other software like CAD and modeling. And yeah, hopefully now you can take something away from this class that's actually useful, not just theory. Now you can actually apply this to the real world. Okay, add it to your resume, add it to your LinkedIn, and then hopefully get a good job. Yeah, so thanks for the reflections. I had a great time reading those. And then reminder to please do the evals. They're due tonight, so please do that. They're going to be helpful for Dr. Barsanti, so we can tailor the class for next year, and then also helpful for me, so I can take your advices on your comments. Okay, that's it. Last lecture. Thank you all. It's truly been a pleasure to be your TA. I can't wait for that day when you guys send me your emails like, hey, I'm doing a numerical method and I just published this paper. All right, so thanks a lot, and get started on your class, on your project. Any questions? Okay, I'm gonna stop sharing.